G'day team. Today I'm just making a few quick videos to do with complex numbers, mostly to remind myself, but if you're somebody else who ends up watching this, I hope it is helpful for you too. My name is Ben Hardless and I'm doing electrical engineering at the University of Southern Queensland. This semester I'm doing Advanced Engineering Mathematics, which is ENM2600, and so there's a lot of material there, and making a little bit of a revision playlist and a set of worked examples I thought might be helpful in exam prep and that sort of thing. So anyway, I digress. Let's get stuck into some revision of vectors, because hopefully you've done vectors in engineering mathematics, the initial one before advanced engineering mathematics. So complex numbers is very closely related to that theory, so we might as well just go over some of the basics. Alright, so a vector is defined as having some start point and really pointing the way to some other place. This point A out in the nether. Now, these points here, really, when you're defining a vector, what you're doing is you're saying, well, we're going across some distance, and we're going up some distance, and what that is some, if you think of it in terms of x and y, we're going some distance in the x direction and we're going some distance in the y direction. Now when we're dealing with vectors, we don't call it x and y necessarily. Normally we express it in terms of unit vectors. So for example, this might be 3 in the I direction, and negative 3i would be off to the going leftwards. So by convention, to the right is positive and up is positive, down and to the left are negative. So we might say we're going positive 3 in the I direction and positive 2 in the j direction, and these little hats are just denoting that these are unit vectors. So what that does is that gives us this vector, which is called OA, funnily enough, vector from O to A, and it's got an arrow on top of it. And what that arrow means, I'll just write it a bit differently. Here we go. The little arrow on top is just meaning that this is a vector value. It's not a scalar. So it not only has a magnitude, which is the length of this arrow, it also has a direction, which is given by this angle here from the 0, where by convention, if I draw a set of standard xy axes and we say, well, this is in the I direction and this is in the j direction, then just like normal, over this way is 0 degrees, up here would be 90 degrees, around to this way would be 180 degrees, and this would be 270 degrees, right? And all the way back to the start is 360, which is equal to 0. Okay, hopefully you already knew that, but just in case, sometimes we got to go over the Billy basic stuff just so we're all really clear about what's happening. Now this vector, but OA, it can be expressed in a couple of different forms. So what we often see it as is, we might see it as OA is equal to 3, 2 in brackets like this. And what this means is 3 in the I direction, 2 in the j direction. That's all that is. We could equally write this as 3i plus 2j. Same thing. Okay, so that's pretty easy. Sometimes you might see this, this OA just represented by a single letter, like we might call it just vector A. That's okay. We can call it whatever we like. We can call it vector Z. We can call it anything. But usually it's we call these points by a letter, right? Reference to some origin. So there has to be some origin defined. So if you just got the vector given to you and it just said, well, 3, 2, vector A is equal to 3, 2, or right, vector 3, 2. Someone just said, oh, vector 3, 2. What that means is that there's some origin, and you need to know where that is, and reference to that origin, you've got a point, and it is 3 in the I direction, 2 in the J direction, and this is the vector that is defined, right? So if we called that vector B, this would be vector B. And usually this point is given, assigned a letter like point B, like that, right? Now we might have multiple vectors, so you might have let's have another vector OB, and we'll say it is -4 and 2. So we can also express that if we just practice -4i plus 2j. Right, or there's nothing wrong with rearranging the order of this, but generally, just so it's nice and easy for us, it's better to keep it in sequence of I, J, K if you're doing three-dimensional ones. But it could equally be written 2j minus 4i, right? That's the same thing. But if you're doing it in the brackets, it has to be in sequence I, J. Now this is only two-dimensional vectors I'm looking at, just for ease of reference, because complex numbers only really has a real and an imaginary component, which is kind of analogous to two-dimensional vectors. That's why I'm not going into the third dimension here. So anyway, back to my example. I tend to trail off, I'm sorry. I've got this vector OA, and I've got this vector OB, and so what does that actually look like? So here's the origin, and we go 3 across like this. I'm making up the scales as I go, so there we go, and 2 up, right? And this point here is A. Cool, righto, no worries. And so usually I just draw it like this, and have and say, well, this I like to do this actually. It's OA, and I just go 3, 2 like that, and this vector is then defined. I might have, and then I've got OB, right? So, that's interesting. Well, OB is -4, 2. So, -4 and 2. Well, -4 is off in this direction, isn't it? So let's do it in a different color, just so you can enjoy the different color. All right. Let's say that's -4. Because we're going off to the left in the I direction, right? Negative I direction. So what we're doing is this is -4i, right? We're heading off this way. Because remember, by convention, positive to the right, negative to the left. And then we're traveling up too. So we're going to end up somewhere over here. And this point here will be point B. And we no longer require this. It was just to help us see how we got there. And this right here is vector OB, which is -4, 2. Now, this is pretty good, isn't it? Righto. Well, my question to you then is, what is vector AB? Now that's this here, this yellow arrow that I've just drawn. That would be for the vector from point A to point B. And so you know what OA is, you know what OB is, but this one isn't connected to the origin. It's from this point A to this point B. So that's interesting. How do we get that? Well, how I like to do it is I just go, well, you know, how did I get from the origin to B? How do I get there this way, right? Just add two vectors up, and I'd go, well, you know, I go from here to there, and I go from there to there, and that's how I get there. So what I'm saying is, well, to get from the origin to B, OB, that's really this distance here, isn't it? Origin to B. That's the same thing as you know, I can also get there, so it's equal to doing this, right? And then we just treat this as basic algebra, where you've got these three variables. So if I rearrange it for AB, and you know, all I'm doing is, well, I'll take OA away from both sides. So if I take OA from this side and I take OA from this side, well, okay, I'm going to be left with, and I'll swap them over left to right. So I'm going to have vector AB is equal to OB, vector OB minus vector OA. Pretty easy, right? So, you know, just to recap that, I've gone, well, you know, I just need to, I've got three things here. I'll just pick one of them and I'll say, oh, well, origin to B I know is defined. I know what that is. So I'll say, well, that's that there, OB. And then I find an alternate route to get there, and then I say it's equal to that. And so I say, well, the other way to get there is this way and this way. So then that's OA and AB. That means that OB is equal to OA plus AB. Anyway, hopefully that made some sense. But we don't have to worry too much about that now. It was just for the sake of doing some rehash. So now what I would like to do is just do tell you something about this vector situation. Come back to the fundamentals of two-dimensional vectors, which is that I think I mentioned before that a vector, and if I didn't, I apologize, a vector is defined by a magnitude and a direction. So magnitude being, you know, for this OA vector is literally the length of this arrow here, right? So that's the size, if you like, the magnitude of it, how big it is, and the direction is given by the angle, in this case theta. So, and you might be thinking, well, how does it have a direction? You've got this right here, vector OA, and it says, well, you've got 3 and 2, so you've got these, you know, a distance in this direction and a distance in this direction, and so you got these two magnitudes, if you like, but where's the direction come into it? And if you just have a bit of a think about it, the direction is defined because, well, if you know two sides of the triangle, then you know the angle, don't you? So we know that tan theta is the opposite over the adjacent. So for us, we can simply find this angle by using the arctan or inverse tangent of the opposite, which is this guy here, because it's opposite from the angle, right? Sorry to make you suck eggs. Opposite over the adjacent, which is beside. Adjacent meaning beside. So 2 over 3, and we would get the angle. So I'll just punch that in on my calculator. Inverse tan 2 over 3, and this is in degrees, by the way, so 33.69 degrees. You may like to express things in radians. Yeah, up to you. So cool. That's all good. Here's an angle. So you do have you do have the magnitude and direction defined. And well, what's the magnitude though? What's you mentioned? I did say the length of that arrow, which is magnitude of OA. So what is the length of that arrow? Well, you know, this is always going to be a right-angled triangle because the J component is always perpendicular to the I component. So you can just do, you know, if you remember the old c squared equals a squared plus b squared minus 2ab cosine theta. If theta is 90 degrees, or let's say phi in this case, where this angle here is phi in this corner here, then what we're doing is we're saying, well, whew, okay, well if phi is equal to 90 degrees, then cosine of phi, cosine of 90 is equal to 0. So this whole part here evaluates to 0. So for a right-angled triangle, you get c squared equals a squared plus b squared. And hopefully that's familiar to you. If not, you may need to go searching on Khan Academy for some more basic unit circle and trig videos, right? Triangle stuff. This is the law of cosines, and it's true for any triangle, but this particular case is just for a right-angled triangle for the reason I've just explained just here. So anyway, we can apply the same concept of finding this hypotenuse, which is OA. So this is this hypotenuse, and we can say, well, the magnitude or the size of that is going to be equal to the square root of the I component squared plus the J component squared. So we can say 3 squared plus 2 squared, right? Which is going to be equal to square root of 9 plus 4 equals square root of 13, and that's it. I won't simplify that further because it's going to be there's going to be some decimal values, and this is a precise answer. So that's the magnitude of OA. So we do have a magnitude and we do have a direction, and that's all of that information is contained in these forms here. So the next video I will start with this same screen, and I will just scroll down and then tell you how that is analogous to complex numbers. Thanks for your time.